just to make sure analogies are used. So one of the prerequisites for this class is physics with trigonometry. So my job isn't here to teach you how trigonometry works. It's to explain how it works for us in biomechanics. How can we use it? How can we understand it so that it's not just another thing we do? We live trigonometry every day. We don't think about it, but we do. So trigonometry is the relationship between sides and angles of 90-degree right triangles. What are the odds all of our triangles are going to be 90 degrees? It's because X, Y, and Z are always perpendicular to each other, and therefore they have to be 90 degrees from each other. So any vector quantity, or any scalar quantity for that matter, is going to probably, law of probability, be some combination of X and Y. It's darn near impossible to get any force or any velocity purely in either positive X, positive Y, negative. I mean, to get it all going exactly in one place. I think last class I said you have 360 degrees of options of application of a force or a speed or something, and only 4 points can it be perfect where you don't have some kind of component of X and Y. And if you have a component of X and Y, those components have to be perpendicular to each other. And if those components are perpendicular to each other, we have a 90-degree triangle. And if we have a 90-degree triangle, we have trigonometry. All right? So just as a reminder, we have a Cartesian plane. This very French dude, Descartes, was trying to explain the position of a spider on his ceiling, because that's what French people did back then, because they didn't have PlayStation. And so he used this quadrant system. You guys are familiar with it, like when you're trying to plot points and stuff like that, right? You'll plot 3, 4, negative, right? How we use it is to communicate direction of what we call a resultant, the so what force, the overall speed. And you get those by measuring. That's what you would measure if you had equipment to measure the force output, the so what force. So to give you an example, if I had a force plate, a three-dimensional force plate that would measure forces in all three planes, when I would jump, it would just give me the so what force. It would say, overall, you imparted this amount of force. But it would also say you imparted that amount of force at this particular angle. From there, the equipment could do it for me, but we have to understand, from there, it's us to be able to figure out, ooh, that's being applied to me in quadrant 2. You see the direction? It doesn't matter if it's down here, it's where is it facing? Am I going north, going south? I could be south of Lafayette but be traveling north. It's all about the direction. So what I need you guys to eventually see is that, oh, I'm in quadrant 2. Right away that tells me whatever the across amount is in the negative direction. And whatever the up amount is in the positive direction. And then based on the angle, I could be able to tell, hey, is it more across, or is it more up, or is it right in the middle? This is a blessing and a curse, because you don't need to see that when all you got to do is plug it in and then it gives you your answer, right? I'm not saying this is bad, but what I'm going to do is take a class or two to explain what exactly is going on and how we can see certain things, because we may not have access to fancy equipment. We have to be able to see it. Okay? All right. So let me give you an example of what we are working towards. A force of 500 pounds is applied at an angle of 20 degrees, FTH. FTH is from the horizon, from the horizontal. That is mechanical terms for positive X. You know what positive X is? That is a engineer or a mechanist anatomical position with numbers. That's all it is. It's an anatomical position so that we know where we're starting once we kind of deviate from it. Okay? So here is the question, trying to put it in layman's terms. We have a force of 500 pounds. Let's say you're pulling a rope onto something and you have a strain gauge and you're able to measure how much you're pulling on the ground. All I'm saying is that a force of 500 pounds is being applied at an angle of 20 degrees from the horizon. That's all we're saying. That's it. Roughly. I don't know exactly where 20 degrees is, but I know it's not here. And halfway would be 45, so it's got to be shallower than halfway, so somewhere around here. Okay? So, right away, without even doing calculations, so that's all I want you to do is just take a picture, pull it up on your notes, or write down 500 pounds, that's what we call a resultant, that's what we would measure, applied at an angle of 20 degrees from positive x from the horizon. That's our direction. That's communicating how it's being applied. Okay? Now I'm going to shift it to the document king. So, our given a force, 500 pounds, given angle theta of 20 degrees from the horizon. Oink, oink. Positive x, negative x. This is just a reminder for myself about our coordinate system. This would also help. Sorry guys, I'm still getting used to this stuff. I used to have a chalkboard. Okay, so remember, all we're setting up is a measured amount of force, influence, is being applied at a certain angle. And I give you that angle, 20 degrees. We could measure it, but I'm giving it to you. What I need you to see, X forces influence X motion, Y forces influence Y motion. Not all of that 500 pounds is trying to shift whatever the heck I'm pulling on across. And some of that 500 pounds is actually trying to lift whatever I'm pulling on up. So I'm getting you to see how there's two different influencers. We're going to have a Y influencer and an X influencer. And so trigonometry is going to say, of that 500 pounds, how much is trying to shift the object into the positive X? And how much of that influence is trying to shift the object in the positive Y? That's it. How do I know that the X and the Y are both positive? Because I'm in quadrant 1. 20 degrees from positive 0 is in quadrant 1, between 0 and 90. That's all given. Like, you don't need to calculate that. Like, you can just see 20 degrees from positive X is in quadrant 1. Quadrant 1, I'm going this way and that way. Okay. If you have your calculators, which your phones have, pull up your calculator, because I just want to show you how this stuff works. And maybe you already know, that's awesome. I didn't know. Make sure your phone can rotate, and then rotate your phone across if you need to know how, and all of a sudden you're going to have the scientific calculator when you rotate it across. And you're going to have buttons like cosine and sine. See it? Okay. So check this out. Here is the scenario. 500 pounds and quadrant 1. All right, so far so good. And look, it might be deeper than 20. I need room. Okay, I need room. I know this is 20. Now, what trigonometry tells us is that I know some of this force is going in the positive X, And also, some of that force is happening in the positive y. In fact, that's what we call concurrent forces, because technically, the forces of the x and the y are happening here at the point of pull, right? At the point of application. Two different directional forces that are happening in the same place. So then we say, well, wait, I thought we were supposed to have a 90-degree triangle to be able to do trig. I don't see a triangle there, but I see the potential because x and y have to be perpendicular, 90 degrees. And this is where ancient mathematicians used computers in their brains because they did a click and drag method, which we do all the time. As long as we don't mess with the size of the arrow, and as long as we don't mess with the angle of the arrow, we can take this x or y, but I like to move my y. We can click and drag this to tip to tail. That's what that is. When you go tip to tail, it's just clicking and dragging and not changing the essence of that component. You're keeping it the same magnitude and you're keeping it in the same direction. But by clicking and dragging it across, now we have a right triangle. That's all that is. Make sense? Okay. Now, life data. I'm not going to say common sense, I'm going to say life data. If this force is at 20 degrees, halfway is 45. So if it's at 20 degrees of pull, wouldn't it make sense that whatever the magnitude is, more of that pull is going to be in the x than in the y? So when we go to check to make sure like our answers make sense, we should have the x component be greater than the y component. If the angle was like 80 degrees from the horizon, we should have more y than x. Like, you should never miss any of these because it's kind of, again, life data. So let's do some trigonometry. I'm going to explain what all this stuff means. The sine function is the opposite side of a given angle. Just like somebody lives across the street from you, in trigonometry, they would be the sine. Cosine is adjacent. Someone lives adjacent to you. Someone's touching your property. So in this example, the x component would be adjacent because it's literally touching or making up that 20 degrees. And the y would be the sine function across the street from the 20 degrees. Cool? This would be my x and this would be my y. So how I would set up the relationship between sines and angles, I'd say the sine function of 20 degrees is directly proportional. Is it sine is opposite over hypotenuse, right? So it would be my y component side over, well, what is my hypotenuse? 500 pounds that I measured. Now before we calculate this to show you this relationship, let's go ahead and do the cosine. Cosine function of 20 degrees. In this case, my adjacent side is going to be my x component. Without solving anything, guys, I know that my x has to be positive. I know that my y has to be positive. And I also know that my x has to be greater than y, and I didn't plug a single thing into my calculator. Does that make sense so far? All right. Now let's go to our calculators and hit 20 and then hit the sign button, and you're going to see a decimal place. Does everybody see, or everybody get it? Should be like 0.3420, blah, blah, blah. That's a percentage. What that means is, whatever vector you have, when it's applied at 20 degrees, 34-ish% of that 500 in this case is going to be in the y. Absolutely. That's what that means. 34% of it is y. So then you say, well, 34% of what? Oh, 500 pounds. That's why you cross multiply. So when you get your percent, you multiply it by 500, and then you're going to actually get the component. The y component of that resultant Let me try to, sorry guys. You know, when I use an ink pen, it's too light. When I use a Sharpie, it's too broad. Now, let's do the x. The x should be, in this example, greater. So let's clear it and do cosine of 20. Look at that percentage. 93%. Which makes sense because it's very shallow. So man, 93% times 500, 469.8. And again, I don't care about decimal places, man. If you're in the ballpark, we're fine. Now, does it check out with my life data? Does it check out with my common sense? Positive, positive, x is greater than y? Absolutely. Here is, in my opinion, the hardest thing it took me a while, and I'm not saying it won't take you a while. You may be like, duh, Campbell. I don't know, I'm weird, I'm different. Our instinct is to want to say that sum of x and y should be our resultant, but that's not how it works. The sum of x and y will always be greater than our resultant, and I'm going to give you two reasons why. The first reason is Pythagoras. Is that the Pythagorean theorem? A plus b is equal to c? So what this would be saying is that x plus y equals 500. That's not how Pythagoras works. What do we have to do to them? We have to square them. The easiest example of why the components of any resultant has to be greater is because the shortest distance between 2 points, in this case the resultant, like let's say we weren't talking force, we were talking distance and displacement. And let's say this is my y and that table's my x, and this is my resultant. Are y'all with me so far? So some of my distance is going to be going to the back of class, and some of my distance is going to be going to your right of class. So far, so good? Do you see what I'm doing here? Okay, watch this. 1, 2, 3 steps to get there. But if I sum the x and y, 1, 2, 3, 4, it's always going to be greater. Does that make sense? The sum of the x, y. So one common mistake is your instinct wants these two numbers to add up to 500. And that's not how trigonometry works. So just because you have the resultant and just because you have one of these doesn't mean you just do math and figure out the other. Cool? All right, let's do another one. We're going to keep it in quadrant 1, and we're going to do 500 at an angle of 45. Now, 45 is halfway. 45 is halfway. So what that should tell you is that whatever my x and y are, they should be the same number, because I'm going equidistant or equal component up and across. Cool? So what I'd like for you to try to do on your own is to just see and then say, well, with life data, the sine of 45 degrees should be the same percentage as the cosine of 45 degrees. Like, doesn't that just make sense? If it's going to be the same number, then the percentage of each should be the same. Anybody else? I'm definitely not going to be as a stickler as my professors at Auburn. But the one thing I will say is we have to at least remind ourselves what we're talking about. So when I put LBS, that sort of reminder said that 500 is a force. Because sometimes we may be talking about velocity. How much of that 75 miles an hour is going up, and how much of that 75 miles an hour is going across? So we always want to kind of put the units to remind ourselves what exactly we're talking about. Okay, what do I know? I know that my x is going to be positive. I know that my y is going to be positive, and I know that my x is going to be equal to my y. Cool. Right? Once you did the trigonometry, what was the y component? Okay, so that was the percentage. That's okay. It's really a different form of the same thing. Once you have the percentage, then all you got to do is multiply by the resultant, right? So that's why we cross multiply. It's 70% of what? And of means multiply, right? 70% of 500. So you're right there. That's the right answer. We just have to take that one extra step to give us a magnitude. Okay? So what's my x and y? They should be the same number. 353. And again, point, that's fine, but I'm more worried about you getting like in the ballpark. I'm more worried about you not getting 500 or not getting 300. Just get me in the ballpark and we're good.
I understand how we get the 353, but what is that?
Okay, then I need to do a better job of explaining. So what that means is, if you pulled, if let's say we had a rope that we can measure how much you're pulling, and you were pulling on an immovable, like we attached it to something that wasn't going to move. What that means is that if you pull, or let's say you have a group of friends that are pulling for this experiment, what that means is that if you pull on that rope with a force of 500 resultant pounds, so what pounds? We measured at 500 at an angle of 45 degrees. What that means is 353 pounds are trying to shift the floor this way, and exactly 353 pounds is trying to shift the floor up. That's all that means. It's weird, huh? But that's what it means, because that's what you're trying to do. You're trying to shift the floor this way, but you're also trying to shift the floor that way by doing it this way. And those are concurrent forces because they're happening at the exact same place, but they're trying to influence motion two different ways. So it's like Pac-Man. This is this. And what I'm trying to talk you through, because I had trouble with it too, it's okay that these two numbers are greater than 500. That's okay, because that's how trigonometry works. It's always going to be greater to sum the two components than the straight line. Okay?
What if it's not a, what is asymmetric?
It can be isometric, yeah. It would be isometric. Okay, let me ask you this. If you got on a scale, and the scale, let's say I got on a scale, and the scale measured 200 pounds, I'm just standing here. The scale's still going to say, hey man, I'm pushing on you with 200 pounds. It's isometric. So if I'm pulling on a fancy scale that can measure my up and across, and it's just going to tell me, hey, you pulled at this amount of force, and you pulled at this angle. I measured that stuff. But 100% could be isometric. Like isometric, still trying to move things. It may not, but you're still trying. Like if I was going to try to like do a max bench press, like I'm still exerting, right, force. In fact, if I don't get it to move and I'm stuck and it doesn't go up or down, I'm pushing on it whatever the weight is while I'm struggling. So it can still exude a force even though there's no motion. That's called statics. So the sum of all the different. So in other words, maybe this will help for some of you that are confused. What we're saying is that whatever I'm pulling this way, the ground is pulling back on me that way. It's not letting me move it. So this is what I would feel from the ground. I would feel a negative. The rope would be trying to yank me that way. Okay, let's do the third one. Let's do what happens when it's more y than x. Seems like a logical play. Next step. Well, before we even do the calculations, let's do some common sense. Angle of 80 degrees, okay, not quite to 90. Still in quadrant 1, x is still going to be positive, y is still going to be positive, but I know going well my y is got to be greater than my x. It's more steep than a cross. Make sense? For quadrant, after we do this example, we're going to flip it up because I think it's going to help. When we get into quadrant 2 examples, we're going to use velocity instead of pounds so that we can kind of visually see different things. But it's the same rules, it's the same exact concepts, but I think mixing out the vectors might help us check for understanding. So when you put in sine of 80 degrees, that's going to be your small piece, and the cosine of 80 degrees, wait, the sine is going to be, the sine, well, it depends on how you do triangle. All right, here we go. Two different forms of the same. Rank. 8 degree. What I did is I usually shortcut to the smallest angle, but it doesn't matter. Click and drag, point, 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 point. So the sine of 80 degrees is going to be my y component, and the cosine of 80 degrees is going to be my x. For those of you that are familiar with rectangles, if this is 80, this has to be 10, right? So you could do the sine of 10 would be your x, instead of the sine of 80 would be your y. It's the same thing. Does that make any sense at all? Okay. So the sine function of 80 degrees is directly proportional, in this case, to my y component, over 500 pounds. Can everybody see when I use the ink pen? Yay. Cosine of 80 degrees, directly proportional to x component, 500 pounds. I know that my y is going to be positive. I know that my x is going to be positive. Then I know that my y is going to be greater than my x without even doing anything in a calculator. Okay? So once again, what I'm trying to work towards is showing us what these cosines and sines, I mean, they got to call them something, they can call them Tom and Jerry. It doesn't matter. It's what they represent. 80 sine gives me a huge percentage, which makes sense. Like, oh, that has to be my y, because it's super steep. 98.48077530122208 of that 500 pounds is trying to influence whatever it is up. That's all that is. So to find out what that force is, that's why we cross multiply. 98.4% of 500 times 500, bang. 492 of the 500 pounds is trying to bring whatever it is up. Again, I don't care about decimal places. Okay, let's do the x. 80 cosine, that should be a small percentage. Yeah, only 17%. That checks out. Right? My y should be greater than my x. Okay. Make this make sense, Campbell. Sometimes, I'm just giving you kind of a practical example. Sometimes understanding trigonometry, not solving for anything, but just understanding resultants and vectors, can help you be a better coach, can help you be a better athletic trainer, understanding forces and injuries. And one time, I was helping a faculty member who doesn't work here anymore move bookshelves, and she was pushing on the bookshelf like this. And what I explained to her was, I said, some of that force is getting in the way of you moving the bookshelf. Because not only was she trying to push it across, but she was also pushing it down. And by pushing it down, she was actually compressing the bookshelf more into the carpet and generating more friction, from which it's harder to slide. So I said, okay, give the same push, and all I'm going to do is lift it up. I won't even pull it across. I lift it up, all of a sudden that sucker started to move. So a lot of times, athletes, we're applying forces at angles and stuff, and trying to be more optimal, trying to be more efficient. Football players, especially when you're talking about linemen and helping linemen, man, it's all about angles. It's It's not necessarily how big and strong you are, it's applying at the right angles. We're training you to be thinkers. I know you already are. Did I show you guys the guy at the convention that was trying to sell me on holograms? Did I tell you that?
Yeah.
Okay. Balance on your left foot. Okay, arm out. Let's go right here so everybody can see. Okay. You look very unbalanced, sir. That's what he said. Don't let me push you down. We're going to do a manual muscle test to prove how unbalanced you are. Don't let me push you down. Don't let me push you down. Oh, gosh, you're so unbalanced. So what you need is, you need this fancy Sharpie. That's going to increase your balance. And now, oh, your muscles are going to work just fine. Arm out. Don't let me push you down. Don't let me push you down. So in both cases, do you remember this trick?
Yeah. I had the sharpness.
So in both cases, I push down. True or false?
True.
I know where you want to go, but I don't want you to go there yet. In both cases, I push down. But in the first case, I bounce. I did this. Down and to his right. I did a negative quadrant 3 resultant because I did down and across, and that's going to pull him over every time. In the other one, I did a quadrant 4 influence, down and to your left. So in essence, my resultant is right through his axis and it's trying to not make it go anywhere. In fact, it's trying to stay away. But you can't see the across.
Well, that's because of sharpness.
Yeah, it was because of sharp. Some other manual resistant tricks people will do, they may like have you put your arms behind and push and pull you down and make you fall down. Another influence too that some manual muscle test tricksters will do, they'll put their whole palm on your arm and then apply their force either distally or proximally, depending on if they want you to be stronger or weaker. There's a lot of crap out there. And none of that means to solve an X. It's just to be able to see what may not be easily seen. Okay? All right, guys, what I'd like for you to do is let's delve into quadrant 2. And here's the trap, or here's the trick. In quadrant 2, our Y will still be positive, but now all of our X are going to be negative. Remember, it's direction. It's not that we owe you, it's the direction. Okay? In addition, a direction of a resultant travels 0, 90, 100, 135, 180. Well, obviously that's not 90-degree triangles, right? But what that's doing is communicating where that resultant is being applied. Once you're in the quadrant, then you can make it into a 90-degree triangle. Meaning, from 0 to 90, I'm in quadrant 2. My X and Y are going to be positive, positive. Between 90 and 180, I'm in quadrant 1. 90 to 180, now I'm in quadrant 2. So I just need to make wherever my angle is a 90-degree triangle with a positive Y and a negative X. Past 180 to 270, now I'm in quadrant 3. Quadrant 3. And I'm going to make my 90-degree triangle negative X, negative Y. And then if I go 270 to 360, I'm in quadrant 4. And I'm going to be positive X, negative Y. Okay? So watch how you do it. If I have, I'm just going to talk you out through these guys. I'm going to talk you through it. If I have an angle, whatever my result, 500 pounds, 500 miles an hour, doesn't matter. At 100 degrees from the horizon, what that's telling me is 90, I'm not there yet, 10. I am 10 degrees away from my nearest axis. 10 degrees. So how we would set that up 10 degrees, not from the horizon, but 10 degrees from positive y. Does that make sense? Okay. Now, here's my 10. My opposite side is going to be my small one, and my adjacent side is going to be my big one. There we go. So when I do my relationships, life data, common sense, my y's got to be greater than my x. It's super steep still. So the sine of 10 degrees should be a very small percentage, and the cosine of 10 degrees should be a big percentage. Now, your calculator will do this for you. If you put like sine of 100 degrees, your calculator is going to do that math and give you a number. It's my job to show you where that number came from. Because it should be cool, kind of weird. Well, wait, 110 degrees, that's not a right angle. But what your calculator does is it subtracts 90 from it. It just does that. Make sense? If you did cosine of 175 degrees, your calculator will subtract from this and figure it out here. Okay? But I want to show you why trigonometry works, because in every quadrant, you've got to have an x and a y. And an x and a y have to be 90 degrees from each other. Okay, what's going to be greater, x or y, in this scenario? You don't even have to solve it. What's going to be bigger, the x component or the y component? Absolutely. Solving it helps to prove it. Right? If you're like, I don't really trust him, do the math and you'll see that the y's got to be bigger. Okay? How about this one? Just write the given. Don't even solve it. A force, well, 500 pounds. I use the same amount just to show you the trends. 500 pounds, angle 225 from the horizon. I want you to tell me the direction of x and y, positive or negative. And then I want you to tell me x and y, greater, equal, or less. That's it, without. Let me do it with you. 225, 0, 90. Did I do 225? 135, guys, sorry, I jumped to quadrant 3. 135, 135. 90, not there yet. 180, too far. 135. Is 135 45 degrees from 90? So that means I'm halfway in quadrant 2. That means my x and y have to be the same. Now, direction-wise, I'm in quadrant 2. I'm still influencing positively here, but now I'm influencing negatively over there. So my x is going to be negative, my y is going to be positive, and my x and y components are going to be the same. We're going to practice, but that's what I need you to see. Last one, 500 pounds, angle of 170. Didn't even do math. 90, not there yet. 180, too far. Let me go back 10 degrees. There I'm at. I'm right here. Positive y, negative x. X got to be greater than y. Look how across that influence is. That's what I need you to see. Anybody throw javelin or discus? Perfect. You know how sometimes when you're throwing, you may have thrown it faster, but it didn't go further because maybe you didn't throw it at the right angle. So in other words, if I throw it too high, it's going to be in the air for a long time. But because it's like going very fast across, it's going to be putting along while it goes across. If I throw it across, it's going to be traveling fast, but it won't be in the air for very long. It's going to hit the ground sooner. It's finding that optimal angle. And I'm not saying optical is 45, but that's what this is all about, is understanding how angles will change components. And in velocities, throwing things, the y component gives you time in the air, and the x component gives you distance. So do you want to cover a lot of distance in a little amount of time? Or do you want to cover a little distance in a lot of time? Probably somewhere in the middle, right? That's what this is about. You won't be able to you're going to have to be able to see things and understand how things influence each other to apply it into the real world. Because in the real world, we won't have fancy equipment. We're going to have this. And we're going to have this. Cool? Who learned a little something new about trigonometry today? Me too. All right, guys. Y'all have a good one.